Good morning from New York. So first, let me thank Joe Chow, Joe, for inviting me, to speak at this wonderful IFAC workshop. So I 100% agree with Joe in saying that the system theory should be a pillar of data science, machine learning, or AI. So I would also add that feedback control should be other pillar of data science, AI, and machine learning. So today I'm going to talk about application topic. That my group at NYU have been working on for the last 5 years or so. So GAN and phase, basically two key concepts in system theory, as Leah mentioned, in his presentation. So here I'm asking following questions. So what happens, when we marry, the system concepts like small GAN with machine learning? So can we do something good, for solving important engineering applications? Here I'm going to address this engineering application called autonomous driving. So this is a joint work with my former PhD students, Meng Zhehua and Weilan Gao. So what's wrong with manual driving? So why do we have to get into the field of autonomous driving? So I'm going to answer this question from the perspective of system theory and machine learning, and provide some results that have been done at NYU. So this is an outline my talk. So mainly I'm going to talk about something called semi-autonomous vehicles. So vehicles that have humans in the loop, like human driver in the loop. So fully automated vehicles are very nice, but it's not going to happen, suddenly, not in 5 years. So in the meantime, we are going to face something called semi-autonomous vehicles with human in the loop. So then we have to develop, some data-driven technology that can allow us to deal with human and the vehicle interactions. So why autonomous driving? So we can see that manual driving has a lot of problems, and we paid a lot of consequence for that. So every year worldwide, over 1.2 million people have died in road crashes, and it turns out that 90% of accidents are attributed to human errors. So this is something we want to avoid by developing autonomous driving technology to improve the safety of the transportation network, and also in terms of cost, financial cost. So on average, so American lost 99 hours a year due to congestions. So translated that number of hours into the cost that's equivalent to roughly 88 billion US dollars in 2019. So, and then not to mention that you have pollution. So the greenhouse gas emissions from transportation has increased by 16% since 1990. So we have to improve so our current transportation network, and by developing something called a connected autonomous vehicle technology. So then this is an interesting field. So I think the control engineers can find a place in this field, and the communication people too. So this is an interdisciplinary field that involves vehicle-to-vehicle communication, vehicle-to-infrastructure communication, and the control will be important component of autonomous driving. So how to use this communication information to design a next generation vehicle technology for autonomous vehicles to achieve something called safer, smarter, greener transportation network. So autonomous vehicles, technology, so it has been shown that it can, significantly reduce, the accidents and save many lives. And it turns out that a lot of companies, here I mentioned Baidu, besides Waymo and Uber. So Baidu started deploying self-driving taxis in Beijing, 2 years ago, so people can get onto and give it a try. So you can see that the reliability of self-driving taxis is almost there. And to improve technology, so you can see that there are 4 modules that we have to pay attention to. So here I mentioned perception, decision making, and path planning, and also control. So I'm going to focus on control and maybe leaving out perception, because when talking about perception system, then we have to mention so latest development in AI, machine learning, deep learning. Here I'm not going to get into that. I just mentioned that for the control system design, so we have to think out of box. So the traditional control theory is model-based. So you have to build precise mathematical models based on data and design control from there. So in the era of AI machine learning, so why don't we go for a direct path? Why can we skip the modeling? Modeling is important for itself, but for some applications, our target is not modeling, our target is control design. So let's go for direct path. From data, let's go to decision making, how to figure out the decisions for autonomous vehicles based on data. So that's what I'm going to talk about today, for semi-autonomous vehicles. All right, so I mentioned that fully autonomous vehicles will be nice, but it's not going to happen suddenly overnight. So you have discovered that there's a lot of study in transportation area, in psychology. People notice that so when you put a human in the vehicle, if you talk about something like a level 3 automation, not a fully automated vehicle. So you put a human driver in the vehicle, but they don't touch the steering wheel. So when some emergency case happen, for example, when the automation system is defected or the load condition suddenly changes, then you have to get a human involved. But you discover that humans are not good at taking over the vehicle suddenly. So transition from automation mode to manual control mode is a very difficult task for human drivers. So that's going to cause problems for for safety. So for this talk, we have to say, why not put human in the loop, get human engaged in the driving task, so that you are going to improve safety during the transition from automation to manual control. So then if we engage human in the loop, so how are you going to develop the vehicle control technology so that you can accommodate this so-called human vehicle interaction, because human behavior are different. I mean, it varies from human driver to driver, but if you put a human driver in the loop, the benefits that you avoid the unsafe transitional behavior, but then eventually they have to deal with the unknown human vehicle interactions. So here we're going to present some results. So this technology is called shared driving. So vehicle controller will coordinate with a human controller to operate jointly the semi-autonomous vehicles. All right. So you need to develop new tools. So here I'm going to present these new tools based on the application of small game machine learning techniques. All right. So let me mention briefly this standard vehicle model. It's based on the dynamic bicycle model from the literature. So I mentioned one paper, the Guian. You can find them detailed mathematical iterations. So the interesting point that even though I do not know necessarily the system matrices, so low is the load curvature is constant, maybe piecewise constant. So I don't know these matrices. So which means the vehicles are different in size, for example, and but I still want to design vehicle controller in the presence of human input TD, so that I can send the so-called output, which is the YC, the lateral offset, which is the distance between center of mass vehicle from the center of the lane. So you want to get a vehicle to track the moving, okay, in a trajectory, which means reduce distance between them, and also at the same time you want to guarantee, okay, internal stability. So this is, okay, a problem called tracking or path following. It's much more complicated than stabilization. So stabilization, which means the design controller to drive, okay, the system to a fixed equilibrium point like origin. So here's trajectory tracking, but you want to, okay, drive the output to zero, not the state. State will converge some, okay, steady state, which is different from zero because the load is non-flat. All right. So there are two inputs. One is the unknown control, human control input. Another is, okay, the vehicle torque input U. So you cannot access information of the human driver. So you only access, okay, the state information of the vehicle X. So this is really, okay, decision making based, okay, partial data. So, but you want to control the vehicle, which means stabilize the entire vehicle and the driver model, and also to send, okay, output to zero. So for the human drive model, okay, so we can come up with some approximate model, okay. So this has been studied, okay, by psychologists and engineers, okay, separately, okay. So it turns out, okay, human driver can make decisions based on two piece of information. One is called a far point angle, one called a near point angle. So near point angle is used, okay, for the tracking, path following of the vehicle. And the far point angle, far view angle is used for, for path following, okay, for the planning of police, okay. So far angle depends on, okay, load curvature, and the near angle depends on the position and the heading angle of the vehicle. So then eventually, you can the human, okay, torque is can be captured by this, okay, linear model. Okay, so this is experiment validate, okay, linear model, okay, by the several people. I mentioned this Santush. Okay, so this is a second order linear model. So torque will be, okay, a function of the state. Okay, the state, of course, driver state is assumed to be unknown, and the same, okay, with the system matrices. All right. So now let's get back to let's go to, okay, the conjugate step. So how do we, okay, use data? The data collected from the vehicle, and to design, okay, shared, okay, steering controller to put the vehicle along the center of the lane and also guarantee stability. So machine learning community care much less about the stability, but this is something that we, okay, control engineering should take that into account, because for engineering systems, if the learning algorithms only promise convergence as the number of data become large, if cannot provide, okay, safety and stability guarantee in the meantime when collect data. So this type of, okay, the machine learning algorithm is not, okay, practically implementable because there's no, okay, guarantee of safety of the driving. So here we have to provide not only, okay, the learning machine learning will converge, okay, to the optimal, for example, decisions as the data are collected, but also we guarantee that each time we learn control law, and this controller will provide, okay, stability, not optimality, but stability for the vehicle. All right, so you can see that small gain is useful, okay, to provide, okay, robustness of stability because we are dealing with an interconnected system. So then you can apply, okay, type of GAN argument, as Lee mentioned, that so if we are able to design, for example, the learning-based controller for the vehicle, so that the gain to be assigned to the vehicle will satisfy the small gain conditions, which means that if I don't know the model for the driver, but the gain is fixed, okay, so the gain is finite, okay, so assume that the driver is a rational driver, so so the system is stable. So then eventually gain is given, even though unknown. So if we are able to assign a gain to the vehicle model so that the gain is smaller, composition is smaller, product is smaller, then eventually the robustness of stability will be guaranteed. Okay, now, so that's called the small gain condition. So the challenge comes from outside that, okay, now how can you do that? How can you assign a gain to a vehicle model based on data? So that's a kind of important problem that has not been addressed in the literature of model-based control, not addressed in the literature of machine learning AI. Because for model-based control theory, when you want to place a pose or eigenvalues of the system to a negative or kind of complex plane, so you have to know the system matrices A and B. So here we don't know A, B, so eventually we have to learn from data how to place a pose in the left half plane. Then for nonlinear model, we have done that also separately. You have to assign a gain. So for nonlinear model, the notion of pole does not make sense. I have talked about the gain. So we can also assign a gain function to nonlinear model based on data. But here, let's stick to linear model first. So you can see that, so here you have to face a lot of uncertainty. So parametric uncertainty, so driver model are not, parameters are unknown because different drivers have different driving behavior. And also we are not going to assume that, so driver state is known because that second order model is, approximation of the real driver model. So eventually I'm not going to assume that we can access to the state information of the driver model. And at the same time, okay, the vehicles, okay, also have, unknown parameters. So this is really a problem, in the spirit of adaptive control. So we're going to do more than adaptive control. We're going to achieve, optimality in the ideal case because we want, to optimize, for example, so a cost function, to save energy, okay. So that's something, we have to do here. So we are going to develop a theory called robust adaptive time programming to approach the problem. So this is really a data-driven, non-model-based approach. So technique I use, so-called robust adaptive time programming, which extends, so dimensions time programming to the case that the system models are known. So make, also involves unknown parameters. And also you have a dynamic uncertainty, which means the model order and the real plant order is different. So the mismatch between them are called dynamic uncertainty. So I have to provide robustness. So in this particular case, dynamic uncertainty is the driver model. So because the vehicle model is the only ideal case, the real plant is the driver vehicle interconnected model. So you have not only have to provide optimality or adaptivity for the vehicle model ideal case, but also have to guarantee robustness with respect to the non-ideal case, which is the driver vehicle interconnected model. All right, so let me go over quickly model-based approach. So in the interest of time, I'm going to go into details. I'm going to skip proofs. If you are interested, you can. I'm going to point to some papers that we published in recent years. So, but for model-based approach, the results is well known, in the field of something called output regression. So output regression, refers to a problem of some touch tracking with disturbance attenuation, disturbance rejection. So you want to achieve a perfect tracking, drive the output to the zero, but also reject disturbances. So disturbance in our case will be the load curvature. So load is now not straight line. So the load curvature is changing, is unknown. So what can you do? So this is but if I assume load curvature is known, then you can apply output regression theory, model-based, to find the solution to solve the problem, asymptotic tracking with a disturbance rejection. So the feed-forward turn depends on the load curvature, and feedback turn will guarantee the so-called internal stability. So the solutions of the control laws is called gain matrices, K U star and K star will be solution of the regulator equation that captures the state behavior of vehicle. So this has been done, I think, as far I know, done by Francis and his advice a long time ago in 1960s. So this is a very important development in conjugate theory to address asymptotic tracking with disturbance rejection. So it's an extension of a PID, by the way. So I skip proof, and then because we can use model-based the controller, so to design data-driven controller, because data-driven controller assumes that even though the optimal controller is exists, but there is unknown. So you have to use data to learn the optimal controller. So I'm going to use beta model-based controller to prove the existence of optimal controller, and then use data to learn it. Okay. So if we assume AB, this is metric unknown, of course. Okay, let me try to mute the speaker if I can. Okay, I muted everyone. So we want to design control not only to stabilize to solve an observation problem, but also to solve some kind of a linear quadratic regulator problem. So we want to achieve not only asymptotic convergence together with disturbance rejection, but also we want to improve transient performance through minimizing linear quadratic regulator cost. So the solution exists. Solution depends on the Ricardi equations. Of course, solution exists, but it's not implementable because AB will be assumed unknown. So we only know the data. So these are optimal solutions. Exist, but how to find them through data, that's a challenge here. All right. So I'm going to talk about robustness briefly. Okay. So then eventually jump to data-driven conjugate design. So this is the model for the driver system. So it's the second order linear model, stable. So but it satisfies some code dispertivity type of properties with the W-like storage functions. So the system will have some kind of gain function. So gain function essentially can be expressed as C2 over C1 square root. So that's the as 2 gain for the driver model. So it's finite, unknown, but so according to the small gain theory, as Professor Lee mentioned, James studies problem for a long time ago for linear gain, classic small gain, and with my advisor Laurent Poily and of course Andrew Thier, we generalized to nonlinear gain for much larger class of state space model. So George James focuses not on state space model but on input output model. So George main focus more on the input behavior. We care both input behavior, also internal behavior. We care about the stability of the state in sense of Lyapunov. So that's also gain function can be arbitrary nonlinear. So George James only assume gain linear functions. So you can see that using small gain, the condition can be guaranteed if you can fulfill this type of small gain condition. Okay, so I'm going to skip this one, but how to satisfy small gain condition in our case, we're going to tune the cost function Q so that the gain can be made as small as possible. Choose a large Q in the linear quadratic regulator cost, we can achieve small gain assignment for the weak model. So that's the technique we can use in the data-driven control design. Okay. All right, so that's the essential question I'm going to address here. We know the optimal controller exists from a linear quadratic regulator theory, from observation theory, but they cannot be implementable because the system metrics are unknown. Can we learn the optimal control from data? The answer is yes. So we have developed over the last 10 years or so with my students, we developed a new theory called the learning-based control theory versus model-based control theory. I'm not saying model-based control theory is not good. I'm saying that for some applications where the knowledge model is not precise, then maybe you want to use data to back up your model-based control design. So I would say, this learning-based control is complementary, okay, to model-based conjugate theory, okay. Vice versa, when you have a more knowledge about model, less knowledge about data, then maybe you should try to turn attention to the model-based conjugate theory. So in the end, I think that the trend will be merge both. We have to use a hybrid mode, okay, which includes both model-based conjugate technique and the learning-based conjugate technique. So this is a tutorial paper we published last year, okay, which describe all the mathematical proofs for the theorem I'm going to state in this presentation. So I'm going to skip proofs. So I'm going to mention data-driven conjugate design. So the base case, which means there's no external steering assistance, we let driver to drive the vehicles as himself. So driver operate vehicles. Of course, we assume that driver does not solve the regulator equations in one shot, but we solve it recursively using this called a policy iteration approach to solve a regulator equation. So recursive approach. So then we are going to compare data-driven shared control with the performance of this base case, driver only driving scenario. So for this base case, of course, you can also prove convergence. So the steady state equation solution of the regulator equation can be approximated by these approximate solutions. All right. So for our case, we're going to consider the unknown system model, AB unknown. So we have to deal with the vehicle and driver interconnected model. So using policy iteration approach to solve the Parametric equations. So we have to this is in the spirit of machine learning. So we do not develop optimal controller based on model knowledge, but they are going to use a model the so-called agent environment interactions, and we are going to appraise, evaluate the policy, then improve policy so recursively. So eventually we are going to find the solution to the Parametric equations. So this policy iteration approach is recursive. So you apply a policy, so like a stabilizing policy controller to the vehicle, but then you are going to evaluate it, using so-called critic components. Then you are going to improve it. The next step is eventually, hopefully, iteratively, so policy will converge to the optimal solution. But each time when we do the policy update, it is based on data only. So that's the idea, data-driven, a control for shared driving. So the essential techniques based Clemens algorithm, recursive method to solve the Ricardo equations. So policy evaluation, policy improvement. So you find a solution, approximate solution to the Ricardo equation. So this one become basically linear matrix equations. The Ricardo equation are linear. So here we assume that KJ. We started with policy known. We are going to evaluate the policy through the cost function or value function, which is happen function. So which is PJ. We evaluate them by improve it. So basically, this is the KJ plus 1 will become dependent on PJ. Then you go back to the policy evaluation iteratively, you can prove convergence. So that's the model-based policy evaluation approach proved by Emma. So how to make it data-driven? So that's our job. So we're going to use this Clemens idea to develop data-driven method. That's number one. Number two, so the regulator equation will also have to convert into data-driven. So because the AB unknown. So here you have to be able to write for example, the modified regulator equations as a linear combination of the basis of the null space of the output mapping. So output mapping is unknown, but the basis function you can find. So eventually, if you're able to compute, for example, the unknown parameters of y, we should be able to find a solution to the regulator equation. So essential problems that how to find the parameter estimate from data, because the generators are known, assumed to be known already. So we are going to use the data-driven auto-evaluation approach, developed by my former student Wei Langao to solve this problem. So we are going to combine both positive iteration based on data and also regulator equations based on data to solve the problem altogether. So let me go through this okay now quickly. So I'm going to differentiate this Lyapunov function, okay, x t or transport pt, a Lyapunov function along system trajectory. You differentiate, then you take integration on both sides over this learning period, collect data over this time period. So then using the Clement method, you can see that these unknown matrices, okay, pj, kj plus 1, no longer depends on the AB matrices. They depend only on the data, because the left-hand side depend data, right-hand side depend data, X is data, QR matrix assumed to be known, KJ is to be known. So KJ plus 1 and PJ appear linearly. So basically, and also of course the last term also is unknown. So you have to find enough data to solve this set of linear equations. Each time collect data, we have one linear equations. If collect the data over multiple time period, we're going to have a sequence of linear equations. Then eventually, when we stop collect data, we stop collect data if the matrix will have a full rank condition. So using corner product, we can rewrite these linear equation into matrix-based form. So psi and phi are data-based matrices. So all the unknown parameters appear linearly, putting column vectors. So when we can find a solution to this linear matrix equation, when the data will be full rank. So we are going to achieve full rank conditions through data. Okay, so eventually that's the procedure. So you have to add some noise, so-called exponent noise, to make sure the data based matrix is full rank. So that's why I cannot. So this is a trick. And the learning period, the collection, the data collection period, that depends on the full rank condition. All right. Okay, so we can also prove convergence. Okay, eventually, so we can prove convergence. Of these solutions as j goes to infinity, the learning step goes to infinity, pj, kj parameter will converge to the optimal solution. We cut the equations, and also we can recover the steady solution of the regulated equation as well. So I'm going to skip the details of the algorithm, which is data-based algorithm. So you have to choose a Q to fine-tune a Q so that you can provide the stability for the robustness of learning. So this is for small game-based application. Then for each Q, we can run this data-driven algorithm to find the near optimal solutions for the cut equation and regulated equations. All right, so I skip a proof. Okay, so we can also prove convergence of the output signals, which means the vehicle will be able to solve this linear keeping problem. So linear keeping error will converge zero, and also internally system is stable, so we can ride the vehicle safely. So there's no instability or unsafety concern about the learning algorithm. So mathematically, we can prove that each learning step, the Ki will Kj will be stable controller. All right. So simulation wise, you can compare the performance with the base case. So when there's only driver who operates the vehicles, you can see that driver vehicles, the error is getting close to the origin, but it's not asymptotic zero. Okay, because the error comes from the the unknown curvature, load curvature. But using the machine learning based technique, we can reduce the error to almost zero. So now applying the machine learning technique, so you add the extra noise to the learning, collect data. Eventually, you stop collect data until some condition is satisfied. Then you implement controller. And then you can see that for first trial, our controller is better. So the error goes down from minus 0.3 to minus 0.1, and for the much better than human driver only. And then for second trial, they all become smaller than the third trial. So each time we improve the controller with the data, you can see that the error gets smaller and smaller, eventually getting close enough to zero. So that's the type of improvement we can see based on data-driven approach. Also, we can apply this the controller to different load situation. It may not be constant curvature, can be piecewise constant curvature. Okay, we can do that. Okay, so we just needed to learn each time load situation changes. Okay, so you can see that the blue line is human driver behavior. Okay, and the other curves might give us a much smaller tracking error than the driver only situation. So you see the error becomes smaller. So this is a cooperative control for third trial. So error is almost close to 0. So my student also implement the controller in animation. So you can see that the gray vehicle is autonomous vehicle. So implemented with our data-driven controller. So we put this vehicle in the context of so-called mixed traffic environment. You have a human-driven vehicles, so I can see that whether or not some vehicle can cooperate with the other vehicles, which means it's not going to crash into the human-driven vehicles. So now you see when the vehicle is running on the straight line, the curvature becomes 0, right? So when the vehicle goes to a circular path, the curvature changes. So there's no human intervention. So we don't measure load curvature. So vehicle has to figure out from the data, figure out control update from data itself. So you can see that the vehicle will be able to run in the urban environment for different kinds of load curvature with changing curvature. So you manage to change lane as well. If there's no can change lane, and when there's a traffic light, so it's going to stop behind the preceding vehicle. When the traffic light changes, so when other vehicles start moving, so it's going to start moving as well. So this is so load curvature also change from non-zero to 0 now. So controller should be able to to modify it by itself. All right. So I have 1 minute to conclude my talk. So let me try to summarize our research. So done mainly by my students at the NYU. So we have proposed a data-driven shared steering control for semi-autonomous vehicles with a human in the loop. So we show that we can definitely combine a system-based technique. Here I use small game, for example, with a learning-based technique. So here is called robust adaptive dynamic programming to design a near optimal and adaptive shared controller for vehicles. So as you know that the adaptive control and the optimal control are two separate fields in control theory. So they are not sometimes they are not merged together. There's reason why they're not merged together. Adaptive optimal. Technically, there's there's some challenges because optimal control assumes the model knowledge, and adaptive control assumes parametric adaptation, but cannot usually do not optimize the cost functions. Okay, so the integration of both fields it can be addressed successfully by means of machine learning technique. So here is the initial trial from our lab along this direction. So I think there are many open problems that we can address in the future. So we can definitely consider nonlinear extensions. So driver model is not linear, vehicle model is never linear. So can we consider fully nonlinear driver vehicle interconnected model? So how about the delay? So humans do not react quickly. There's always delay. So then vehicle should take into account the robustness to human reaction delay. So this one has not been taken into account in the design of a machine learning based technique. So also we have to generalize to multiple vehicle scenario like platooning vehicles. So vehicle will talk to each other by vehicle to vehicle communications, to form a tight platoon to improve transportation efficiency. And also, we needed to kind of carry out experimental tests. So this one I cannot do that New York City, not in my lab. So we have to work together with companies. That's it. Thank you so much, for your attention. Okay, any questions are welcome. Here's my email address. Thank you.